Hello everyone, welcome to my third video series on physics for CSIR, NET and GATE competitive exams. In this video series, we will be discussing on Lagrangian and Hamiltonian dynamics. I have also released two video series on op-amp and partition function. So please note that in this video series, we will be focusing on how to solve rather than to understand more about the physics. So in Lagrangian formulation, we have this generalized coordinate and we have this generalized velocity. Then if the system is conservative, then we can write the Lagrangian as kinetic energy minus potential energy. So if we know the Lagrangian, then we can write the equation of motion as like this. This is the equation of motion. Then if we know the Lagrangian, we can even find out the generalized momentum, which is denoted by P subscript K. And this is given by the partial derivative of the Lagrangian with respect to the generalized velocity. In Hamiltonian formulation, suppose we know the Lagrangian, then we can find out the Hamiltonian using this expression. Once we know the Hamiltonian, we can write the equation of motion, and in Hamiltonian formulation, it's a set of first order differential equation given by this. So these are the formulas which we'll be using, and down the line we might be needing some more formula. So when we are solving the numericals, we'll discuss. Okay, now let's solve some numericals. In this question, we are given the Lagrangian and Px, Py are the generalized momenta, and we have to find a canonical equation of motion. So first, let us write the Lagrangian. The Lagrangian is mx dot y dot minus m omega naught square xy. So from this Lagrangian, we can find the generalized momenta. So Px will be del L by del x dot, which is my dot, and similarly Py will be del x, the derivative of the Lagrangian with respect to y dot. So this will be mx dot. So from this we can express as y dot is equal to Px by m and x dot is equal to Py by m. So then we can find the Hamiltonian. So the Hamiltonian is given by summation of q dot k p k minus the Lagrangian. So if the summation will run from x and for x and y, so it will be x dot px plus y dot py minus mx dot y dot plus m omega naught square xy. So this is the Hamiltonian. Now I can write the equation of motion. So p x dot will be minus of del h by del x. So if I differentiate, I think I'll be getting m omega naught square y. Similarly for py dot, you'll get del x del h by del y, which is equal to minus m omega naught x. So we have this and this. Now if we see the options here, I think it is matching with option C. In this question, we are given a projectile motion of mass 1 kilo launched at 30 degrees from the horizontal direction at t equals 0, and the time of flight is capital T, and initial speed is 10 meter per second, and we have to find the action integral for the entire flight. Now action integral is given by the integral of the Lagrangian with respect to time. So here, since they have asked from t equals 0 to capital T, so the limit of the integration will be like this. Now the Lagrangian has to be integrated with respect to time. First, let us draw a projectile motion here. So this is the projectile motion. Let's say it's in XY plane. The initial velocity is 10 meter per second. So it is projected at an angle 30. Now for this, the kinetic energy will be given by half x dot square plus y dot square. And the potential energy will be given by mgy. So if I write the Lagrangian, it will be half mx dot square plus y dot square minus mgy. Now the Lagrangian is in terms of x dot, y dot and y, but the integration, the action integral, we have to differentiate with respect to time. So we need to express the Lagrangian in terms of time. To express that, we had to revisit our high school physics on projectile motion. Now we know that in projectile motion, the horizontal component of the velocity remains constant. So x dot here will be u of cos of 30. So u is 10, cos 30 is root 3 by 2. So x dot will be 5 root 3. Now the y dot, that is the vertical component of the velocity, it changes with time. So what we can do is, we can use the formula s is equal to ut plus half at square. So this one will be uyt plus half of at square. So if I substitute this, uy is given by u of sine of 30 t minus of half gt square. Now u is 10, sine 30 is half, so t minus half g is 10 t square. So from this you get 5t minus 5 of t square. So this is the expression of y, because we'll be needing y because it's there in the Lagrangian. So from this, if I differentiate again, I'll get y dot. So it will be 5 minus 10 of t square. So now you have got the expression of y and y dot in terms of t. You have got the expression of x dot. Now you can substitute this value in the Lagrangian. So when you substitute, you can pause the video and do the substitution. I'm writing the final expression here. So you'll get an expression something like this: 100t square minus 100t plus 50. Now you can solve the action integral here. So it will be 0 to t dt. So we need to know the t, capital T. So to solve this capital T, you can use the time of flight formula, that is 2v sine theta by g. So 2 into 10 into sine theta is, sine 30 is half here, g is half. Then so you'll get t equals 1. So a becomes 0 to 1, 100t square minus 100t plus 50 dt. So you can do this integration, and finally you'll get 200 by 6. So this is 100 by 3, which is 33.3. So this is the answer. In this question, we are given that this term is a constant of motion. So if I differentiate this term with respect to time, it should give 0. And the system is an isotropic harmonic oscillator with the Lagrangian given by this expression, and we have to find the value of alpha. Now, the first thing we have to do is, let us write the Lagrangian here. So Lagrangian is half m x dot square plus y dot square minus half k square plus y square. From this Lagrangian, we can find the equation of motion. Now there are two coordinates here, x and y. So for x, it will be d by dt of del L x dot minus x. So if I solve this, I will be getting, if I differentiate, I'll get mx dot, and here I will get plus of kx. So this will be equal to 0. Mx double dot plus kx is equal to 0. So I can write x double dot is equal to minus km into x. Now let's do it for the y. So for y, this will be the equation of motion. Then this will be equal to 0. So if I differentiate, I'll get here my double dot plus k of y is equal to 0. So y double dot is equal to minus kmy. So this is these are the two equations of motion. Now let us come back to the term which is constant of motion. So constant of motion is x dot y dot plus alpha xy. So since this is constant of motion, if I differentiate it with respect to time, it should give 0. So if I differentiate, I'll get x double dot y dot plus y double dot x dot plus alpha x dot y plus alpha xy dot is equal to 0. Now let us substitute x double dot and y double dot in this equation. So I will have minus km xy dot minus km x dot y plus, I can write this, I can take alpha outside, so it will be x dot y plus xy dot is equal to 0. Now if I rearrange this, I can write minus k by m. I can take this term to be common, plus x dot y dot plus alpha xy dot plus x dot y plus xy dot equals 0. Now these two terms I can cancel out, and alpha is equal to minus k by m. This is alpha is equal to plus k by m. So k by m, yes, option A is the correct answer. In this question, we are given a particle of mass m, which is moving in a frictionless 2-dimension in r theta plane, and it is acted upon by a force, and this force, it's a central force. If pr, p theta are the generalized momenta, we have to find out the derivative of pr. So basically this is in the polar coordinate system, and for polar coordinate system, the Hamiltonian is given by p r square by 2m plus p theta square by 2m r square plus v of r. So I advise you to get familiarized with the expressions of the Hamiltonian in different coordinate systems. It will be very useful. Now using this Hamiltonian, I can write dpr by dt, that is pr dot is equal to minus Hamiltonian of delta differentiation with respect to r. So if I differentiate this, I will get p theta square 2m r cube, and you'll have a factor 2 here, so that minus minus become plus. then minus del V by del R. Now 2 cancels out. Now this del V by del R, this is equal to the force. So what we can do is we can substitute the expression of the force here. So PR dot becomes P theta square mr cube minus of, actually it's minus del V by del R. So I can substitute that K by 2R cube. So what can I do? I can take 2mr cube common. So 1, 2 factor will be here minus Km. So this is the answer, and I think it is matching with option D. In this question, we are given an oscillating system. Here we have a mass m with a charge plus q, and it is placed at a d distance from an conducting plane, and we have to find the Hamiltonian. So here we don't have any loss in the system, so H, the Hamiltonian, we can write as a sum of the kinetic energy and the potential energy term. So the kinetic energy is given by P theta square by 2ml square. This is a standard expression of the kinetic energy for an oscillating system for simple pendulum. Now for potential energy, it will be a contribution from two different terms. One is from gravitation and another one is from electrostatic potential. So first we will electrostatic. So first we will deal with gravitation. So this is the system here. Suppose if it is at an angle theta here, then this distance will be L cos theta, and the gap is D. So the height from Z equals 0 will be D minus L cos theta. So V from gravitation will be mg D minus L cos theta. Next, for electrostatic, we have to use the concept of image. Now, suppose if I have a conducting plane, if I have a charged particle here at a distance, let's say x, then the potential energy of this system will be equivalent to half of this system. So in our case, x is equal to this, because that is the distance above this z equals 0 plane. So the potential energy V of, due to electrostatic, it will be half of 1 by 4 pi epsilon naught minus of q square, then into twice of D minus L cos theta. So now we have got the potential energy and we have got the kinetic energy also. Now we are in the position to write the Hamiltonian. So Hamiltonian will be equal to P theta square by 2ml square, then minus of q square. So this one here you'll have, 16 here, 16 pi epsilon naught D minus L cos theta plus mg D minus L cos theta. So I think it is matching with option D. Here we are given the Lagrangian of a particle of mass m, and it is told that the particle oscillates with energy E, and the time period of oscillation is given by this, and we have to find the value of A. Now this question is very much different to what we have solved till now. So to solve this, let me give you some concept. There is a method called action angle method. In this method, we can determine the time period of oscillation without actually solving the equation of motion. So what we generally do is we calculate an integral of pi dqi. This is the action phase integral, and this, after calculating this integral, if we differentiate it with respect to the energy, then we get the time period of oscillation. Now, for this system, the first thing we can do is, from the Lagrangian, we can write the Hamiltonian of this system. So Hamiltonian will be, since it does not have any loss factor, I think we can directly write like this: mx dot square plus lambda x to the power 4. Now, this equation I can write as px square by 2m plus lambda x to the power 4. So Hamilton, they have given the total energy E, so this will be equal to E. Then I can express this px as root over 2m E minus lambda x to the power 4. So now we have got the expression of px. Now we can find the action phase integral J, which is integral of root over 2m E minus lambda x to the power 4 dx. Now this integral is for the whole cycle. So this is basically a non-linear oscillator. So what we can do is we can use the symmetry of the phase portrait and calculate for only single quadrant, and we can take four times of that particular integration, and we will be getting the total area. So if I substitute x, x is equal to 0. If I substitute x is equal to 0 in this equation, then px is equal to 0. If px is equal to 0, then x will be equal to e by lambda to the power 1 by 4. Let me just write it down properly. 1 by 4. So what can I do is I can take this as 4 times of integral from 0 to e lambda to the power 1 by 4. Then root over 2m e minus lambda x to the power 4 dx. So this is the integral. Now to find the time period, I'll use this formula. So I have to differentiate this j with respect to e. Now to differentiate this, we can use the Leibniz method, where you can take this differentiation inside the integral. So using that technique, my differentiation will be 4 integral of 0 e divided by lambda to the power 1 by 4. So if I differentiate this, I'll get 1 by 2 root over 2m e minus lambda x to the power 4 dx. Then here you'll get another 2m factor. So 2 cancels out. And this m, I can take it inside, so it will be 2 by m. then you'll have the expression 4 integration of 0 e by lambda to the power 1 by 4, sorry, dx. Here dx should be written on top. So dx divided by root over 2 by m e minus lambda x to the power 4. Now this is dj by de, which is nothing but the time period. Now if you compare this integration and the integration given in the question, then we can see that the integration is the same, so a will be equal to 4. So a equals 4. This is the final answer. In this question, we are given the Lagrangian and we have to find the Hamiltonian. And you can see in all these options that they have expressed the Hamiltonian in terms of the generalized momentum and the generalized coordinate. So we have, first we can find the generalized momentum. So this will be del L by del x dot, minus will be, no minus here. So if I differentiate, then I'll get 2ax dot. So from here you can write x dot as px by 2a. Similarly, py will be given by this differentiation. So it will be 2by dot. So y dot is equal to p by 2 of b. Now we can write the Hamiltonian. So Hamiltonian will be given by summation of q dot k pk minus the Lagrangian. So this summation will run over x and y. So Hamiltonian x dot px plus y dot py minus of ax dot square plus, sorry, minus of by dot square. Now I can substitute the expression of x dot and y dot. So this one will be, if I substitute here, I'll get px square by 2a plus py square by 2b minus of, oh, there is one more term in the Lagrangian. It's minus cxy. I forgot to put this. Now here I can write a px square by 4a square. So a will cancel out. Similarly for the next term, minus b py square by 4b square. So this one will cancel out. And finally we have cxy. Now this term and this term we can simplify, and similarly this term and this term we can simplify. So on simplification we will get px square by, I think 4, yes, 4a plus py square by 4b. Let me write it down properly. Then you have minus c, x and y. So this is the Hamiltonian. So it is matching with option A. In this question, we are given the Hamiltonian here, and P and Q are the generalized coordinate and momentum. And for this initial condition, the generalized coordinate is directly proportional to t to the power alpha, and we have to find the value of alpha. So let's write the Hamiltonian first. Hamiltonian is equal to p square 2m plus kq into t. Now we will find the equation of motions. So q dot will be equal to del h by del p. So this becomes p by m Similarly, for P dot, it is minus del H by del Q. So this becomes minus K of T. So these are the equation of motion. First, let us take the momentum part. So P dot is equal to minus KT. So if I integrate this, I'll get P is equal to minus KT square plus some constant, I'll call it C1. Now for at T equals 0, P is equal to 0. If I substitute this, then I'll get C1 is equal to 0. So P is equal to minus KT squared. Now let's come back to Q dot. Q dot is equal to P by M. So I can substitute this, it will be minus K by M T square. So if you differentiate this, then Q becomes minus K by M T cube plus some constant C2. Now if I substitute initial condition that T equals 0, Q equals 0, so C2 will be 0. So from this I can write Q is directly proportional to T to the power cube. So here alpha, so alpha is 3. This question is a bit different from whatever we have solved till now, because generally we take the Lagrangian and calculate the Hamiltonian. But in this question, the Hamiltonian is given and we have to calculate the corresponding Lagrangian. So we know that Hamiltonian is given by summation of Q dot K pk minus of L. So if I just rearrange this, then I'll get this. So pk minus h. So with this formula, let us proceed. So the Lagrangian will be Q dot P minus of alpha P square Q to the power 4 2 minus beta by Q square. So this is the Lagrangian. But I think it is not matching with any of the options. So now what we can do is we can use some trick here, like, okay, what will be Q dot? Q dot will be this. So if I differentiate this, then I think I will get what? P, so it will be alpha P Q to the power 4. So this is, so now one thing we can notice, in all the options, they have not expressed in terms of P. So I think from here we can get P is equal to Q dot alpha Q dot divided by alpha Q to the power 4. So this we can substitute. So if I substitute this in the Lagrangian, maybe I can use a different color. So Lagrangian will be equal to, so Q dot, instead of P, I can write Q dot alpha, Q dot divided by alpha into Q to the power 4 minus alpha, then P square alpha by 2, P square I can write Q dot square alpha square Q to the power. So it will be 8 into Q to the power 4 minus beta by Q square. So here alpha, we can cancel this, and if I cancel this, I'll get 4. So it will be L is equal to Q dot square alpha Q to the power 4 minus, here you have Q dot square 2 alpha Q to the power 4 minus beta by Q to the power 2. So if I simplify this, I think I will get Q dot square alpha Q to the power 4 2 here, minus beta q to the power 2. So this, I think option A is the correct answer. In this question, we are given the Lagrangian and we have to find the Hamiltonian. So Lagrangian is given by m by 2 v square. So I can write that as r dot square plus c r vector dot r dot vector minus v of r. So this is the Lagrangian. Now we have to write a Hamiltonian for this. So we can use the formula summation of qk dot pk minus the Lagrangian. So if I substitute, okay, it will be r dot p. Here they have given pc is a canonical momentum, so I will use this notation pc here, minus of m by 2 r dot square plus c r vector dot r vector dot minus v of r. Now here we can assume that the position vector and the velocity vector are in the same direction. So this dot product, we can replace it like this: m by 2 r dot square plus c r into r dot minus v of r. So this is the assumption we are taking. Now we can substitute, because in the options they have not given in terms of r dot. So what we will do is, so pc will be given by the derivative of the Lagrangian with respect to r dot. So if I differentiate, it will be m r dot plus c of r. So from this I can write r dot as pc minus c of r divided by m. So what I'll do, I'll substitute this in the Lagrangian expression. So if I substitute here, it will be pc minus cr divided by m into pc minus m by 2 pc minus cr by m whole square plus cr into pc minus cr divided by m and minus of vr. Okay, by the way, this has to be plus because Lagrangian is minus vr, so this has to be plus. Yes, this one has to be plus. So now you can pause the video and you can simplify this expression, and finally you'll get the answer: 1 by 2m pc minus cr whole square plus vr. So this is the simplified expression, and I think it is matching with option B. In this question, we are given a system where there is a spring and through a wire it is attached to a mass m, and this wire is over a pulley system, and we have to find the angular frequency at small oscillation condition. Now, since the wire is inextensible, whatever the displacement x is happening for the spring, the same displacement will be happening for the mass m. And suppose if x naught is the equilibrium displacement of the spring, then under equilibrium mg will be equal to k times x naught. We'll be using this later when we derive the equation of motion. Now the kinetic energy. So kinetic energy, one will be due to the motion of the mass, so it will be x dot square. At the same time, we'll have one kinetic energy due to the rotational motion of the pulley, so it will be I omega square, and we know that omega is equal to v by radius a, so this is x dot by a. So if I substitute that, I'll have half mx dot square plus half a square I x dot square. So maybe I can rearrange this: half m plus I by a square into x dot. So this is my kinetic energy term. For the potential energy, we will have two potential energy terms. One is due to the spring and one is due to the gravitational potential energy. So for the spring, I can write the equilibrium length into x square, and for gravitation, I can write mgx. So if I combine these two, the Lagrangian will be equal to half m plus I by a square x dot square minus of half k x dot x naught plus x then plus of mgx. Okay, now we can write the equation of motion. So equation of motion is given by d by dt of del L by x dot minus of del L by x, which is equal to 0. Now if I differentiate the Lagrangian with respect to x dot, I will get m plus I by a square into x dot. Then if I differentiate with respect to x, I will get plus, sorry, here one square should be there. So k x naught plus x, then you'll have one minus mg here. Now here I have written the equilibrium condition that mg is equal to kx naught. Because of that, we can cancel this. So your final equation of motion will be m plus I a square into x double dot plus kx. This is equal to 0. So from this equation, we can write omega is equal to root over k divided by m plus I a square. So if I rearrange this, I will get root over k a square divided by m a square plus I. So this is the angular frequency, and I think it is matching with option B. In this question, we are given in Lagrangian and we have to find the correct options here. Now, if you see the Lagrangian, you can see that Q1 and Q2 terms are not present, but the Q1 dot and Q2 dot terms are present. But in the case of Q3, we can see a term here. So, if in the Lagrangian, if Qk is absent, not Q dot k, but Qk is absent, then we say it is cyclic. So whenever it is cyclic, then the corresponding generalized momenta will be constant of motion. That means the derivative of this p will be 0. So from this Lagrangian, we can say that Q2 and Q1, they are cyclic. So I can say P2 and P3, they will be constant of motion. So what is P3? Sorry, P1. Let me write it properly. P1, they are constant of motion. So what P1 will be given by the Lagrangian of derivative of the Lagrangian with respect to Q1 dot. So this will be M Q1 dot plus capital M Q2 dot. And I think one more term is there, plus K Q3. So this will be constant. Similarly, for P2, it will be derivative of the Lagrangian with respect to Q2 dot. So if I differentiate, I'll get Q2 dot plus M Q1 dot. This will be constant. Now, let us write the equation of motion for Q3. So it will be d by dt of del L by Q3 dot minus of del L by Q3, which is equal to 0. So if I differentiate this one will be 0 and minus, it will be K Q1 dot is equal to 0. So from this equation, I can refer that Q1 is a constant. Now, if Q1 is constant, then this one also will be 0. Okay, I can use this equation. If Q1 is constant, then this one will be 0. So that means Q dot 2 will be constant. If Q dot 2 is constant, then Q2 is linear. So I can write here Q2 will be linear. Now, if Q2 is linear, then this one will be a constant. Q dot will be constant. And Q1 is already constant, so this one will be 0. So this is 0, this is constant. So definitely Q3 will be constant. So Q3 will be constant. So what we have here is Q1 is constant, Q3 is constant, and Q2 is linear. So I think in the option A, they have mentioned 2 coordinates remains constant and 1 evolves linearly. So this is the correct answer. So in this question, we are given Hamiltonian and there are 2 generalized coordinates P1 and P2 and Q1 and Q2, and P1 and P2 are the respective canonical momenta. And we have to find the Lagrangian. So Lagrangian, we can use this formula Qk dot Pk minus H. So here you'll have Q1 dot P1 plus Q2 dot P2 minus of P1 P2 into minus Q1 Q2. Now from the options, we can see that they are all expressed in terms of Q or Q dot. So what we can do is we can use the equation of motion. So Q1 dot is equal to the derivative of the Hamiltonian with respect to P1. So I'll get here P2. So from this we can write P2 is equal to Q1 dot. Similarly, Q2 dot is equal to del H by del P2. So you'll get P1 here. So you can write P1 is equal to Q2 dot. Now if you substitute back in this Lagrangian, so this one will be Q1 dot Q2 dot plus Q2 dot Q1 dot. Then instead of P1 and P2, I can write Q2 dot and Q1 dot minus Q1 Q2. So these 2 terms will cancel out. So you have Q1 dot Q2 dot minus of Q1 Q2. So this is the Lagrangian. I think it is matching with option D. This question is similar to the previous one where the Hamiltonian is given and we have to find the Lagrangian. So we can use a similar method. So Lagrangian will be equal to x dot p minus the Hamiltonian. So x dot p minus p squared by 2m e to the power minus x by a minus v of x. Now I can use the equation of motion to express p in terms of x dot. So x dot is given by the derivative of the Hamiltonian with respect to p. So this one I'll get p by m e to the power minus x by a. So from this, p is equal to m into x dot e to the power x by a. So I can substitute this p here in the Lagrangian. So this one will give me x dot square e to the power x by a minus m square x dot square e to the power 2x by a divided by 2m, and you have 1 e to the power minus x by a here. So, and here we have minus v by x. So this m will cancel out, and if I cancel this, I can remove this 2 factor here. So if I simplify, we will get x dot square e to the power x by a divided by 2 minus v of x. So this is the Lagrangian. And I think it is matching with option A. Yes, it is matching with option A. In this question, we are given the Lagrangian and we have to find the conserved momentum here. So there is one of this term. If we differentiate with respect to time, it will give 0. So to find out which one is the correct option, first we need to find the equation of motion. So there are 3 variables, x, y, and z. So for x, the corresponding equation of motion, this will be given by this minus del L by del x. So this is equal to d by dt. And if we differentiate, we'll get mx dot, then minus of 2 alpha, this will be equal to 0. So from this, we get mx double dot is equal to 2 of alpha. Now this one should be plus, so it will be minus 2 of alpha. Similarly, we can write for y. So this one will be equal to, I'm directly writing the equation of motion. So if we differentiate y, then we'll get mz dot by 2. Then if I differentiate y, it will be plus of 3 alpha. This is equal to 0. So I have mz double dot is equal to minus 6 alpha. Now you can write for the z using this equation, z dot minus del L by del z, and you will get, I'm writing the final equation here, you'll get my double dot is equal to tan of alpha. So you have 3 equations here, one here, another one here, and you have this one here. So now using these 3 options, 3 equation of motions, we will check the options one by one. So if I check option A, so if I differentiate this with respect to time, then I will get m2x double dot plus mz double dot. So if I substitute mx double dot, it will be, so 2 here, so minus 2 alpha, then z double dot is minus of 6 alpha. So you get minus of 10 alpha, which is not equal to 0. So option A is not a conserved momentum. Let's go for the second one. So if I differentiate the second option, I have 2 mx double dot plus my double dot plus mz double dot. So it will be minus 4 alpha. Then you have plus 10 alpha, and you have minus 6 alpha, which is equal to 0. So the second option, when we differentiate with respect to time, it is 0. That means option B is a conserved momentum. In this question, we are given the Lagrangian and we have to find action along the classical path from t equals 0 to t equals t naught, and the path is from x equals 0 to x equals x naught. So first, the Lagrangian is given by half x dot square minus x square. Now we are interested in this integral. A is equal to 0 to t naught L Lagrangian into dt. Now we have to express the Lagrangian in terms of time in order to do this integration. So to express that, we need to write the equation of motion x dot minus L by x equals 0. So if I differentiate this, I will get x dot, then you'll get, if I differentiate, you'll get plus of x equals 0. So the equation of motion will look like this. Now this equation of motion is similar to the equation of motion of harmonic oscillator with a frequency omega square equals 1. So we can write the general solution as x is equal to a sine of t plus b cos of t. Now this is the general solution. So what can I do? I can substitute the initial condition. So when x at t equals 0, it is 0. So if I substitute this, then from this condition I can get b equals 0. Now what about x at t equals t naught? It is equal to x naught. So that gives, since b is already 0, so a sine t naught. So from this I can get a to be x naught divided by sine of t naught. So now I can get the final solution. So x as a function of t will be given by x naught divided by sine of t naught into sine of t. So this is a general solution. Now once I get x as a function of t, I can find x dot. X dot will be equal to sine of t naught into cos of t. Now I have got x and x dot in terms of time. So I can substitute this into the Lagrangian. So now I have, this is equal to half. I can take the constant outside. So it will be x naught sine t naught. And this one will be cos square t minus sine square t. So this one you can simplify as x naught sine t naught into cos of 2t. So now we have the Lagrangian as a function of t. So we can integrate now. So it is from 0 to t naught, half of x naught sine t naught into cos of 2t dt. So I can take the constant outside. So it will be x naught by 2 sine t naught. So cos 2t, the integration is sine 2t by 2 from 0 to t naught. So this gives x naught by 2 sine t naught into sine of 2t naught divided by 2. So what can I do? I can express the sine 2t naught into 2 sine t naught and cos t naught. So sine will cancel out. So finally I will get, okay, by By the way, this one should be square. So this one should be square. This one also square. Square here, square here, square, square, square here. And here also you have square. Then following the step, the sine 2t0 will be 2 sine t0 cos t0. So you'll get x0 square. Maybe I can write with a different colors the final answer. So it will be a is equal to x0 square. You'll have a factor 4 here, and then you'll have cos by sine. So it will be one more 2 factor will be coming from the 2 sine theta. So 2 factor will be coming here. Then it will be cot of t0. So 2 cancels out. So your final answer is x0 square cot t0 by 2. So this is the final answer. So I think it is matching with option C. In this question, we are given that a particle of mass m is constant to move on the surface of a paraboloid, and we have it is under the influence of the gravity, and we have to find angular speed about the z-axis is proportional to which of the following option. So let me draw the surface here. The surface of a paraboloid will look something like this. Now, and let's say this is the Cartesian coordinate x, y, and z. Now, if you try to solve using Cartesian coordinate, the problem might be a bit complex. So what we can do is we can solve in cylindrical coordinates. Now, I advise you to know the different forms of Lagrangian in different types of coordinates. It will be very useful. So for cylindrical coordinate, the kinetic energy term is given by, I'm taking here as r, theta, and z as the variables in the cylindrical coordinate. So it will be, the second term will be r square theta dot square plus z square. And for the potential energy, we can directly use mgz. So this is a Lagrangian. Now, using this Lagrangian, we can see that it does not contain any term theta here. So this theta dot is here, but theta is not here. So theta becomes cyclic. So when theta is cyclic, p theta will be constant. Since p theta is constant, so and p theta is equal to the derivative of Lagrangian with respect to theta dot. So this one will be half mr square 2 theta dot. So this is mr square theta dot. So this term is constant. So since this term is constant, mr square theta dot is constant, I'll just denote it by c1. So if I integrate this, I'll get mr square. Okay, no need to integrate. I think they're asking for angular speed. So theta dot is angular speed. So theta dot is equal to c1 by mr square. Right. So mr square means it is directly proportional to 1 by r square. Now what is this 1 by r square? Now in cylindrical coordinate, r is the radial position. So now we can use this equation, x square plus y square is equal to a into z. Now x we can write as r cos theta whole square plus r sine theta whole square. This is equal to az. So if I substitute this, you get r square is equal to az. So using this expression, I can write it is directly inversely proportional to 1 by z. So option C is the correct answer. Here we are given a system of mass m1 and m2 tied with a string, m2 is under the influence of gravity, and m1 is undergoing a circular motion. So r0 is the equilibrium length, and when we give a slight displacement of epsilon, much lesser than r0, then it's found that the system oscillate about r0, and we have to find the frequency of oscillation. Now, in such type of problem, the first thing you have to remember is the length of the string is constant. This is constant. So when this is constant, then the rate at which the length is changing here and here will be same, because the length has to be constant. That's the trick. Then now we can write the kinetic energy. So kinetic energy, I can write m1 plus m2 r dot square. I am writing r dot for both m1 and m2 because the length of the string is constant, so their velocity will be same. Another is due to the circular motion of m1, so it will be m half of m1 r squared theta dot square. This is due to the circular motion. What about the potential energy? So potential energy will be experienced by m2, so it will be minus m2g L minus r, and here L is the length of the string. Now I have got both the kinetic energy and the potential energy, so I can write the Lagrangian. It will be T minus V, so this becomes half m1 plus m2 r dot square plus half m1 r square theta dot square plus of m2g L minus r. So this is the Lagrangian. Now from the Lagrangian we can see that theta is cyclic. So since theta is cyclic, the momentum corresponding to theta will be constant of motion. So that part we'll use it later. For now, let us try to write the equation of motion. So equation of motion will be given by d by dt of del L r dot minus del L by del r. This is equal to 0. So if I substitute, I think I can directly write m1 plus m2 r double dot, then it will be minus of m1 r theta dot square. Then here this one will give minus m2g, but because of this the minus, then we'll get here plus m2g. This is equal to 0. So this is the equation of motion. Now in this equation of motion, I have this theta dot term. So since it is oscillating in r, somehow I have to substitute this in terms of r. So to do that, what we can do is we can see theta is cyclic. So if theta is cyclic, the momentum corresponding to theta will be constant of motion. So that we can use. So m1 r squared theta dot, this is nothing but p of theta. We can get p theta by differentiating the Lagrangian with respect to theta dot. So this is constant of time. So, and in the question they have given that r0 is the equilibrium length. So I can write this one as m1 r0 square is equal to theta naught dot. So using this relation, I can get theta dot is equal to r0 by r whole square theta naught dot. Now again, the problem here is I don't know the information of this theta naught. This I don't know. So to find out theta naught, what I can do is I can consider the equilibrium condition. So in the equilibrium condition, what will happen is the centripetal force will be balanced by the weight. So using that concept, so centripetal force of m1 will be m1 v square by r. So v I can write in terms of theta omega, that is theta dot. So I can write this one as m1 r naught theta naught dot square. This is equal to mg. So this is the equilibrium condition. So from here I can write theta naught dot square. This is equal to, oh, this one should be n2. So m2 by m1 g divided by r naught. So now you have got this theta naught here. So this you can substitute it here. Then finally you'll get theta dot square. This is equal to r naught. Okay, maybe it's better to multiply r here. So this expression using the above two, you will get r naught by r whole cube m2 n1 g. Now you can use this expression and substitute it here. Now you can pause the video. You can substitute this one. Then after the substitution, maybe it will be better if you go to the next slide. So I'll go to the next slide because the equation is a bit lengthy. So let me write down the equation here again. It is m1 plus m2 r double dot minus m1 r1 theta dot, sorry, not r1, it's r. So theta dot square plus m2g is equal to 0. And we already got r theta dot whole square is equal to r naught by r whole cube m2 m1 into g. So I'll substitute this to this term. So on substitution, I'll get m1 plus m2 r double dot minus m1. So this one will be r naught by r whole cube m2 divided by m1g plus m2g is equal to 0. So m1 can cancel out. Now this is my equation of motion. Now what I'll do is this r, I will displace it by some epsilon, where epsilon is much lesser than r naught. Then r double dot will be equal to epsilon double dot. So my equation of motion will look something like this in terms of, sorry, epsilon. My equation of motion will look something like m1 m2 epsilon double dot minus r naught by r naught plus epsilon whole cube m2g plus m2g. Now what can I do is I can take this term. From here I can take r naught common and I can bring this term into the numerator and I can expand this one. So m1 plus m2 epsilon double dot minus, so r naught cube will be there, and this one will be, if wait a second, Here what I'll do is I'll take the R0 cube to be outside. Then this one will be 1 plus epsilon by R0 to the power minus 3. So R0 cube, it cancels out. So M2G plus M2G, this is equal to 0. So since epsilon is very less than R0, I can expand this. So this one double dot minus. So this one will become 1 minus 3 epsilon R0 M2G plus M2G. This is equal to 0. So here we can see this one will cancel out with this. So M1 plus M2 epsilon double dot plus 3 R0 M2G epsilon. This is equal to 0. Now we have the differential equation in terms of the simple harmonic motion. So from here we can write omega is equal to root over 3 by R0 M2G divided by M1 plus M2. So you can simplify this as 3 M2G divided by R0 into M1 plus M2. So this is the frequency. In this question, we are given a simple pendulum and this is oscillating. So theta is changing with respect to time, but the support where the simple pendulum is hung, it is also undergoing a oscillation ZT. So Z is changing with respect to time. So they have given a harmonic disturbance A sine omega t. So the theta equation of motion is given here and we are told to find out what is this Ft. Now to solve this, suppose we have the coordinate of this as x and z. So what is x here? X will be given by L sine of, this is theta. So L sine theta is the x. And what about z? Z is L cos of theta plus the zt, because this z is oscillating. Now from this I can find out x dot. X dot will be L cos theta, theta dot, and z dot will be L sine theta, theta dot plus z dot. And what is z? Z is already given here, A sine omega t. So I can write L sine theta, theta dot plus A omega cos of omega t. Now you have got x, z, x dot and z dot. Now we can write the Lagrangian. So Lagrangian will be equal to half of m x dot square plus z dot square. Then this is under the influence of the gravity. So the potential we can write as plus, because minus will be plus. So mgz. So this is the Lagrangian. Now I will substitute x dot, z dot and z so that we will have the equation in terms of theta. So you can pause the video, substitute x dot, z dot and z. I'm writing the final expression here. So your Lagrangian will be half m L square theta dot square plus A square omega square cos square omega t minus of 2A omega L theta dot sine theta cos omega t. It's a very lengthy expression, but it's an easy one. Mg L cos theta plus A sine omega t. So this is your Lagrangian. Okay, and the square bracket should be here. Fine. So this is the Lagrangian. Now we can find the equation of motion in terms of theta. So it will be d by dt of del L by theta dot minus del L by del theta. So if you substitute the corresponding expression, you will get, okay, so you can do this exercise. I'm writing the final equation of motion because it's a bit lengthy, and it's a very easy exercise. So you will get a final expression like this: L theta double dot plus sine of theta a omega square sine omega t plus g. This is equal to 0. Now if you compare this equation with this equation, then f of t is equal to minus a omega square sine omega t. So this is matching with option D. Thank you for watching the video. We'll continue in the next second part of this video series.